Dr. Vimla Thetan Rathina Sabapati, Professor and Head of the Department of Electronics and Communication Engineering in Aditya Institute of Technology, Coimbatore. Doctorate in the field of crypt analysis in Government College of Technology, Coimbatore. Postdoctoral Fellow in the Department of Information Engineering, University of Padova, Italy. He is very much interested in research area of cryptography, crypt analysis, electromagnetic interference, compatibility, antenna design, wireless sensor network and communication. He has published papers in international journals and international national conferences. He is a reviewer of journals like DRDO, WSCAS, International Journal of Network Security, and also have a membership in professional bodies like CRSI, IACR, and Computer Society of India.
Welcome to UGC lecture series, Communication Electronics for Applied Electronics. In the last session, we have discussed about how to generate an AM wave and then how to detect the AM wave. That is, we have generated double sideband with full carrier. In the today's session, we are going to see about the balanced modulator and then single sideband generation. If we take the balanced modulator, this balanced modulator is used to generate double sideband with suppressed carrier. Why we want to suppress the carrier? We already seen that if you transmit an AM signal, it have carrier and two sidebands, and that too the two sidebands convey the same information. Also, if you transmit the carrier, the total power is not utilized effectively, only 33% of the power is utilized effectively. So, now we are going to see about another type of modulator which is called as balanced modulator that will suppress the carrier. If you take a device, for example a diode or a transistor, this may be operated in linear region or non-linear region. If you take a diode, diode is a piecewise linear device. If you operate the device in a certain voltage, it will act as a linear. It is also possible to operate the device, that is diode, in non-linear region. As well as if you take an amplifier, we use transistor. The transistor will be operated in linear region in case of amplifier. It is also possible to operate the transistor in non-linear region. Now, we will see what happens if a device operates in linear region or non-linear region, and then thereafter we move to the balanced modulator. Let us take a simple system. This may be a diode or a transistor. Now, it is operated in linear region. For this device, we are applying a signal Vm cos omega mt. Since this device operates in linear region, based on this type of this network, for example, if it is an amplifier network or an alternator network, this device will process only this component, amplitude component. And what happened to the frequency component? This frequency component will be same as the input. This amplitude V may vary, that depends on this type of the network. Here please make a note, there is no change in the frequency, only in the amplitude. Suppose if the device operates in non-linear region, we will see what happened to the frequency component. Let us consider the same signal Vm cos omega mt is applied to a non-linear component. The output of this non-linear network will contain the frequency cos omega mt, that is omega mt is the fundamental frequency. Along with this, we will have multiples of n omega m. For example, if you provide 1 kilohertz input, the output will contain 1 kilohertz and multiples of 1 kilohertz, for example 2 kilohertz, 3 kilohertz, and go on. So, the output contains infinite frequency component based on the non-linearity. So, this principle can be used for frequency multiplier or to raise the level of the frequency. Using this concept, now we are going to see about the balanced modulator, and here we have seen only one frequency component that is applied to a nonlinear circuit. If we apply two frequencies, now what happens? Let us consider we are applying another signal of cos omega ct. We are applying another frequency to a nonlinear circuit. So what happened to the output? Output contains omega m, omega c, that is the fundamental frequency of the two signals, and then it contains multiples of omega m and multiples of omega c, and along with this we will have sum of the frequencies and difference of the frequencies, and then we will have multiples of sum and multiples of difference. So we will have infinite number of frequency component if you provide two frequencies to a nonlinear network. We are going to apply this concept in generating a double sideband suppressed carrier. If we consider a diode or a transistor that operates in linear region, then if you apply voltage V, the resultant current will be I, and the relationship between the current and voltage will be given by I equal to BV if it is a linear device. Even if it is a linear device, for example, if you take a class A amplifier, so the relationship between the current and voltage is given by I equal to A plus BV. This says that the voltage gets scaled by some parameter B. Along with that we have one constant. Mathematically we will call this as a constant, and electronically we call this as a DC value. Suppose if the device, the transistor or diode, operates in nonlinear region, now what happened to the relationship between the current and the voltage? If you see here, the current depends on that constant, and then the voltage, first power of voltage, second power of voltage, and higher powers. So it goes on based on the nonlinearity. If two separate voltages are applied to the device, now what happens? We already seen that this is the relation between the current and voltage for a single voltage if you apply one voltage. If you apply two voltages, now we are applying V1 and V2. So what happens? It gets summed. So instead of V we have V1 plus V2, and here we have V1 plus V2. If V1 is a sinusoidal signal and V2 is also a sinusoidal signal, now what happened to the current? See here, the current contains these components. So after expanding this, so here this one V1 plus V2 square, so we have to expand using A plus B the whole square equation, that is A square plus B square plus 2AB. So this is A square, this is B square, this is 2AB. And after simplifying using the mathematical expressions, trigonometric expressions, if you take sine square, you have to replace in terms of cos, and then if you take this is a form sine A sine B, and after simplifying this is the final expression. If you see the final expression, here we have constant term, here we have a constant term, and here we have the signal with frequency omega, and then here we have sine rho, this is due to V2, and the frequency gets doubled here, that is 2 omega and 2 rho, and here difference of the frequencies, and here sum of the frequencies. That is, the output current contains this much number of frequency components: omega, 2 omega, 2 omega, and then 2 rho, and sum and difference. Now we are going to apply this concept in a balanced modulator. This is a simple circuit that shows the balanced modulator, which is constructed using a diode. If you see the circuit here, we are going to operate these two diodes in nonlinear region. Why? So we have to generate higher frequency components, that is some frequency component and difference frequency component as well as harmonics. And this one is a transformer, audio transformer, and here this is an audio transformer at the output, and this is also an audio transformer for coupling the carrier signal frequency. So, we are providing the two signals, audio signal and radio signal, to the balanced modulator, and now we are going to see how the double sideband is generated with the suppressed carrier. This is the circuit constructed using diode, and this is the balanced modulator constructed using FET. Here we have two FETs, FET 1 and FET 2. The same circuit, instead of diode we have field effect transistor, and these two devices are also will be operated in nonlinear region. And here we have the audio signal and the radio signal, which is going to be the carrier. Let us consider this is V1 and this is V2. What is the purpose of this transformer? Here it is a central tap transformer. If we apply V2 here this V2 gets coupled to the secondary, and the voltage at this point will be in phase with this input. But if we consider the voltage at this terminal, here this will be out of phase with respect to the input. So, if I apply V2 here I will get minus V2, that is 180 degree out of phase, whereas here if I apply V2 here I will get only V2, that is in phase. Here we are applying the carrier signal, which is V1. So, what is the voltage applied to the gate of this field effect transistor? That is sum of the voltages V1 and V2. And if we consider this FET 2, since the voltage is 180 degree out of phase with respect to the input, here I will have minus V2, this will be added with V1, that is it becomes V1 minus V2, and that is applied to the field effect transistor 2. The current, the output current, this is ID1, that is the current flowing through the drain 1, and ID2 is the current flowing through the drain 2. The same current will be also flowing through this primary of the transformer, this output transformer. So, here if we consider this ID1, that will be equal to IP1, and if we consider ID2, the current flowing in this section will be equal to IP2. And what about the resultant current I? Since both the currents are flowing in opposite direction, the current I1 will be the difference of ID1 and ID2. Now, we are going to apply that concept what I have discussed, that is nonlinearity concept here. So, here we are applying two voltages V1 plus V2 and V1 minus V2. So, what about the ID1? That depends on the sum of the voltages V1 plus V2, that is first power and the second power. If we consider that current ID2, this depends on the difference of the voltages V1 minus V2, that is first power of V1 minus V2 and the second power of V1 minus V2. So, if we expand this ID1, that is using the concept of A plus B the whole square. So, here I will get A plus BV1 plus BV2 plus CV1 square plus CVT square plus 2CV1 V2. The same way for ID2. The only difference is here we are going to expand using the expression A minus B the whole square. So, here if we consider these two currents, there is slight difference, and now we want to find out the resultant current I1, which is nothing but the difference of ID1 and ID2. So, simply take the difference. If I subtract these two equations, what happens? This factor gets cancelled and this also gets cancelled, but this one gets double because here we are going to find out the difference. So, this becomes 2VB2 and these factors gets cancelled, and here this factor becomes, if you find the difference of these two, this becomes 4CV1 V2. Now, what is V1? V1 is nothing but the carrier signal, that is of high frequency with frequency omega c, and if we consider V2, that is the audio frequency signal with frequency omega m. So, consider this V1 and V2 as V1 sin omega ct and V2 as sin omega mt, that is the carrier signal and the message signal. You apply this in these two expressions and find out the difference. or simply you can directly apply in the final expression. See what happens. So here we have 2b v2 plus 4c v1 v2, which is nothing but this is nothing but the message signal, and here we have 4c v1 v2. So here we have to take the product of the message signal and the carrier signal, and after applying that mathematical trigonometry concept, sin A sin B formula, so we have simplified this one. So if you see this output here, we have, what about this one, the message signal frequency component. Along with this, here we have the difference of the frequency component and some frequency component. We have 3 components totally. So here we have a tuned circuit. The purpose of this tuned circuit is to separate this component, separate this message signal frequency, and also using a proper filter you can eliminate any one of the frequency component. So what is the purpose of the balanced modulator? To generate a double sideband with suppressed carrier. But if you see that final expression, we have only the difference component, that is, this is nothing but the lower sideband and this is nothing but the upper sideband. We don't have any carrier, so we have suppressed the carrier successfully. Now if you see that spectrum of an AM, it contains carrier and 2 sidebands, but whereas if you consider the spectrum of an balanced modulator, the carrier gets suppressed. So this is the output spectrum of a balanced modulator. We have seen about the balanced modulator. Now next we are going to see about the single sideband generation. Why we go for single sideband generation? If you take a double sideband, both the sidebands contains the same information. It is not necessary to send the same information in the 2 sidebands. So we can suppress any one of the sidebands. Now we are going to see how to generate a single sideband generation. There are 2 methods. One is filter method and the other one is phase shift method. If we consider this is the filter method, here we have a balanced modulator. For this balanced modulator, there are 2 inputs, main inputs. One is crystal oscillator, which act as a carrier, and another one is audio input, that is the message signal. Just now we have seen what is the purpose of the balanced modulator. What is the purpose? Just to generate a double sideband with suppressed carrier. If you see the output at this point, that is, we will have 2 components. One is some frequency component, another one will be difference frequency component. Now we are going to suppress any one of this sideband using a filter. If you use a high pass filter, then upper sideband will be removed. If you use a low pass filter, then we can remove that lower sideband. So based on the requirement, whether we require an upper sideband or lower sideband, we can select the appropriate filter. Here we have 2 filters, suppression for one sideband, this is a suppression for the other sideband. If we consider this output of the balanced modulator, we will have the 2 components. Now we can suppress any one of the component. If you see that spectrum, so this is the spectrum of double sideband with carrier, but here using a balanced modulator we have suppressed the carrier, and then using the filter technique we are going to suppress any one of the sideband. Now I am going to remove the lower sideband. So lower sideband is removed. We have only the upper sideband. So this can be transmitted. The efficiency of the transmitter is automatically improved. If we want to suppress the upper sideband, here we are transmitting only the lower sideband. So we can easily generate a single sideband using a balanced modulator and a filter. And the next one, we are going to generate the same single sideband using another method called phase shift method. This is the block diagram of the single sideband generation using phase shift method. If you see, this is the, we have 2 balanced modulator, modulator 1 and balanced modulator 2. We have 2 balanced modulators, and what all the inputs we require for the balanced modulators? One is carrier and another one will be the message signal. Here this is the carrier for both the modulator M1 and M2. But if you see the carrier is directly applied to the balanced modulator 2, but whereas the same carrier is 90 degree shifted in phase and then applied to the balanced modulator 1. But if we consider that audio signal, this is the audio signal, we are applying the audio signal directly to the balanced modulator 1. But if we consider this audio signal, this signal is shifted in phase by 90 degree and then we are applying to the balanced modulator 2. See here, for this one, for any one of the modulator, we are shifting either message or carrier and we are applying to the modulator. What is the necessity for doing this shift? You can clearly understand from this one. If we consider that output of a balanced modulator, it contains difference frequency component and sum frequency component. But if we consider this V1, see here, this is V1. What about the carrier? The carrier is shifted by 90 degree and then applied. So, the carrier's frequency gets shifted by 90 degree. So, here also the carrier signal gets shifted by 90 degree. But if we consider this signal V2, so what happens? Here the carrier is applied directly, but the audio signal is shifted by 90 degree, that is the message signal. So, this is the carrier and the message signal gets shifted by 90 degree. So, these two are the outputs of two balanced modulators and we are applying these two outputs to an adder. So, what is the output of an adder? It is simply sum of V1 and V2. Just after doing some mathematical manipulations, this is the final expressions. Here this is the lower side band and this is the upper side band and this is the lower side band and this is the upper side band. If you see here these two component, here this component 90 degree is leading and whereas here this component is 90 degree lagging. So, what about the total phase shift between these two component? It is 180 degree. Hence, if we add these two components, so what happens? Of course, they are equal in magnitude, but 180 degree out of phase, automatically these two components gets cancelled. But if we consider these two components, so what happens? They are equal in magnitude as well as in phase. So, if you add these two component, what happens? The amplitude gets doubled and here we have minus. Of course, you can use it as a multiplication factor. So, in this way we can generate a single side band with suppressed carrier. Here there is no carrier, we have only one side band. Now, let us see the output spectrum of the single side band. Here carrier is suppressed using a balanced modulator and then the lower side band is also suppressed. In this case, here we have the upper side band. If you want to generate the lower side band, what we have to do? Just you simply change the phase shift. Here if we consider this case, here we are applying the carrier directly to this modulator and whereas this one 90 degree phase shifted we are applying to this modulator. And here if you interchange the carrier and the audio frequency and then if you provide the alternate phase shift, then it is possible to generate the lower side band. What is the disadvantage of this phase shift method? Here we have two balanced modulators and each balanced modulator should have equal sensitivity and then exact same output. And also we are providing a phase shift network for both the carrier as well as the audio signal. It is very difficult to maintain the phase shift at 90 degree at all the times. So, this is one of the disadvantages of this phase shift method. And in the today's class we have discussed about the balanced modulator and in single sideband modulator. In case of balanced modulator, we have suppressed the carrier and then we have transmitted the two sidebands. Why we are doing this? In order to improve the efficiency of the transmitted signal. But if we consider this double sideband, we are transmitting the same information in the two sidebands, so we go for a single sideband. So, we have generated the single sidebands using two methods. One is filter method and then phase shift method. If you take the advantage of this single sideband method, the efficiency of the transmitter is improved. But if you take the disadvantage of this single sideband receiver, the receiver cost is very high. A normal person cannot afford a single sideband receiver. But this can be compensated at the transmitter. If you use a good transmitter, SSB transmitter, now we can go for a good quality receiver also. So, this is the main disadvantage of this SSB. The cost of the transmitter is very high. Next one is questions for the today's session. What is meant by balanced modulator? And explain how single sideband modulation can be generated using different techniques, and what are the single sideband applications. Usually this single sideband is used in mobile receivers as well as in submarine communications. Thank you.